Hello. So in this video, we're going to talk a little more about kind of special kinds of Fourier series. And so in particular, what we'll call Fourier sine or Fourier cosine series. And so these are just Fourier series where, right, we're only computing coefficients with respect to kind of the sine terms or the cosine terms. And so of course, we can say, well, let's compute a Fourier series, but let's ignore half the terms. So that's in practice how we'll say, compute like a Fourier sine series. But a little more generally, we can make sense of these Fourier sine and cosine series by considering certain extensions of functions, right? So if we have a function that's only defined for the interval 0 to L, so for example, right, so 0, L, and we have some function like this, okay? Generally, if we want to compute a Fourier series, right, we need to know what the function looks like over here as well, okay? Because most of our setup says, well, right, compute the Fourier series for this entire interval. And so going from this information, right, the function defined over here to the function defined over here, we actually have a few options. And depending on how we construct this extension, when we compute the Fourier series, depending on the extension, we will only get sine or cosine terms. And so, yeah, so we'll talk, that's the focus for this section. So in particular, what we're going to do is we're going to start talking about what even and odd functions are and get some kind of terminology out of the way. Then we'll look at these, what we're calling these Fourier sine series, which again are Fourier series where you only have sine terms showing up. We'll then talk about Fourier cosine series. And then we'll talk a little about kind of convergence of these things and what you can say about kind of essentially continuity of a Fourier sine or cosine series. Okay. Yeah, so the starting point is talking about even and odd functions. So what are even and odd functions? So a function is even if you plug in kind of negative the argument, you get back the original function. Right, so the classical kind of example is cosine of x, right? Because say cosine of x is even because cosine of minus x is equal to cosine of x. Okay. So even functions, in a sense, they're symmetric across the kind of x equals 0 with the y-axis. And then a function is odd if kind of you plug in negative x or negative the argument. In a sense, you can kind of pull that negative sign out. And so the kind of classic example, sine of x is odd because sine of negative x is equal to minus sine of x. Okay. And so in some sense, right, for odd functions, right, what's the symmetry that's happening? Well, you can think of odd functions as, so if you kind of reflect the graph of the function across the y-axis, right, so you reflect it, and then you reflect it across the x-axis, that's going to be the image that you get. Okay. But kind of quantitatively and how this is used in practice is, right, this condition. This is what defines an odd function. Okay, so a neat little fact is that no matter what function you have, you can write it as a sum of an odd and an even function. Okay, which stated like that may seem, I don't know, you may have your thoughts about whether or not that's believable. But it's actually not kind of terrible to write out. Right, so the claim is, doesn't matter what this function is. you can write this function as a sum of an odd function and an even function. So the question is, well, right, how might we prove that? One way is to just explicitly write out what these pieces are. And so in particular, this odd piece is going to be f of x minus f of minus x over 2. Okay. And the even piece is going to be f of x plus f of minus x over 2. Okay. And so let me actually move this over here and then move this over here. Right, so there are 2 facts to verify, or I guess 3 facts to verify. First is that f is the sum of this and this, right? But for that, you can just write, well, what is f odd plus f even? Okay. Writing out the definition, you're going to get this plus this, right? That's just kind of the definition of f odd and f even. Okay, and so if you do kind of work through the arithmetic, right, you have a minus f of minus x over 2 plus a positive f of minus x over 2. So these 2 pieces are going to cancel. Otherwise, we have an f of x over 2 plus f of x over 2. And that's going to give us exactly f of x. Okay. So, right, summing up these 2 things, we get our function back. The other 2 things to verify are that f odd is odd and f even is even. Right, but to do that, we can just say, okay, well, plug in negative x. What do we get? And so, for example, you say what, right? So f odd of minus x, for this to be odd, we want this thing be equal to minus f odd of x, right? Coming from this definition. Okay, but if we plug in negative x, that's going to be f of minus x minus f of minus x over 2. So of course this becomes, so we won't mess with this, minus, and then we can pull this minus sign out so that we end up with minus f of x minus f of minus x over 2. And this is exactly minus f odd of x. Okay, so you can do the same thing with the even piece, right? But it's a neat little fact that, you know, it doesn't matter what the function is, you can decompose it in this way. Okay, so that's all about even and odd functions. Cool. So the next thing that we're going to talk about is, well, you know, suppose your function is only defined, say, on the positive x-axis or the interval 0 to L. Okay, and so especially in computing Fourier series, we'd like to work with a function defined from negative L to L, just because that's how kind of our framework's set up. Okay, so what we would like to do is have a way of going from a function defined on kind of this half interval, right? And so this is kind of like the picture I had before, right? So maybe this is your function. And what you would like to do is take the definition of your function and then extend it so that it's defined over the entire interval. Okay? And so given with what we just talked about, there are kind of 2 natural choices. Okay? So the first one is what we'll call an even extension. And so for this kind of extension, what we're doing is we're saying, well, here's our function, and let's define kind of the function over here, so that if you look at the function kind of on the entire interval, then it will be even. Okay, and so Great. So how do we do that? We say, well, take negative values of x, right? So values of x over here. And then what is the value of the function at those negative kind of x values? Well, the value of f is going to be the value of f at minus x. Okay, and so because x is negative, minus x, this is going to be positive. Okay, so then this is going to be a value kind of from where we've originally defined our function. Okay, so for example, so kind of this even extension, right? What we can do is say, okay, well, maybe this point right here. What is the right function value to assign right here so that we end up with an even function? Well, by this definition, we say, okay, well, the value of the function there should be the value of the function at minus x. So if we're right here, we look at the value for minus x, the function value there, and something like that. Okay, and so then the picture you get should be something like this. Okay, up to artistic abilities. Okay, and so maybe another way of phrasing this is, well, if we want to compute an even extension or construct the even extension, right, just take the graph of your function and reflect it across the y-axis. Okay, so that's one option. Another option is to take an odd extension. And so here, what we're going to do is we're going to say, again, right, for negative values of x, what is the value of the function there? Well, the value of the function for negative x is going to be the value of the function for the corresponding kind of positive x value, but then we're going to flip it across the x-axis, right? So if we want to know the value of the odd extension here, we say, okay, what's the value over here? That's that. Okay, so this right here, this is f of minus x. And so then we say, okay, but we want an odd extension, so we need to take minus this value. So then, right, take that, see what is there, take this function value, say reflect it over there, and then reflect it across the x-axis. Okay, so we can draw things out, and oh boy, so the odd extension is going to look something like that. Okay, but these are two different ways, these are just two ways to extend the definition of the function to the entire interval negative L to L in a way that works well with Fourier series. Okay, of course, there are plenty of other ways that we can extend the definition, right? One possibility is to say, well, if we want to kind of extend the definition of this function over here, just say the value of the function over here is 0, right? That would be another way to extend the definition of the function. But here, for kind of the cases that we'll be looking at, the extensions that we care about are going to be even or odd. And again, we like these because they play well with Fourier series, and that's really the tool that we want to develop. Okay, cool. Cool. So then the question is, great. We can take these even and odd extensions or work with a given even or odd function. And so the question is, if we have an even or odd function, right, what are the Fourier coefficients? Okay. Well, the one observation is, right, so if your function is odd, meaning that if you plug in negative x, you're going to get negative f of x. If your function is odd, you would expect that you might expect that it can be written right in terms of an odd function, or just if you try to break it up into pieces, all of these pieces will be odd pieces. Okay, and so in particular, right, sine, all of these pieces here, these are also odd, right? So if we have an odd function, maybe in its Fourier series, we'd expect only odd pieces to arise, and we wouldn't expect any even pieces to show up. Okay. And so practice, what that means is, well, if you have an odd function or the odd extension of a function, and you try to compute the coefficients for cosine, these coefficients should just be 0, right? We wouldn't expect even pieces to show up for our odd function. And likewise, if your function is even, then if you look at its Fourier series, right, the pieces in that Fourier series should probably also be even themselves, right? Or you might not expect odd functions to show up in the Fourier series for an even function. Okay, so if your function is even, right, then the Fourier series should probably only have even terms. Okay, so what does that look like in terms of the coefficients? Well, b sub n is going to be 0. Okay, so our Fourier series is just going to have cosine terms. Okay, and so these can all be computed rather explicitly, and we'll do that here in a second. Okay, but the point here is, right, functions can be even or odd or neither, and so, right, we expect some sort of connection between even and oddness in the pieces that are showing up in the Fourier series. Okay. So what we're going to do now is we're going to start the discussion with Fourier sine series. Okay, in particular, right, can you decompose a function into just sine terms? What conditions let you do that? Where do these things arise, etc. So kind of the observation right from before, well, if f is defined on this interval from negative L to L and f is odd, then its Fourier series should only have sine terms. If instead f is just defined on the kind of that half interval 0 to L, and we want to compute some sort of Fourier series, right? In a sense, we have two options. Okay, one, we can just compute its Fourier series only using sine terms, right? So only get these sine coefficients on the interval 0 to L, and say, great, that's our Fourier series. And then another option is to first extend the definition of f from 0 to L to the entire interval negative L to L. Okay, so take the odd extension of f, and then compute the Fourier series of that odd extension on that entire interval. Okay. And so, right, by this first fact, we're here. If we do this process, take the odd extension, compute the Fourier series, we expect that there aren't any cosine terms. Okay, and so then the series will only have sine terms. And so it turns out that, right, either of these ways of thinking of this problem and like computing these coefficients, either of these ways will give you the same series. Okay, so one way to think of it is, well, if anyone says compute the Fourier series using only sine terms, implicitly what you're doing is you're first taking the odd extension of the function to this interval negative L to L, and then computing the Fourier series on that entire interval. Okay. Cool. And so, right, so the claim was, well, if you have an odd function and you try to compute kind of the cosine terms, the coefficients, they should just be 0. Okay, and so sure, that matches some intuition, but that's also something that we can actually compute and see rather explicitly. Okay, so if we have an odd function on the interval negative L to L, what we can do is just go ahead and try to compute, for example, the constant term a naught. Okay, so how does that go? Well, a naught we're computing for this entire interval. Okay, so that's just going to be, right, 1 over the length of the interval times the integral of your function over that interval, or the average function value. And so what we can do here is we can split up this integral to go from negative L to 0, and then 0 to L. So what does that look like? This is what we end up with. Okay. And so now what we can do is change variables. Okay, and so in particular, here, we're doing the change of variables x to negative x. Okay? And so what that's going to result in is, well, 0 is going to go to 0, minus L is going to go to L, and then dx, this is going to become, so d of minus x or minus dx. Okay? And so what we can do is we'll plug those pieces in, right? And so we end up with this expression, right? So x goes to negative x, dx, we're looking at d of negative x, and then otherwise the bounds have changed, and we're not doing anything with this piece. Okay? But now what we can do is use a property, or the fact that f is an odd function. Right, because so f is an odd function, f of negative x, right, so odd function means f of negative x is equal to minus f of x. So here, this is going to give us a negative sign. Okay, so we're going to pull this negative out. It's going to give us a negative. This negative we're going to pull out, and so it's going to give us another negative. Otherwise, if we want to flip the bounds of this integral, so that instead from L to 0, it's from 0 to L, we can flip the bounds and then pick up another negative. Right, so after we do this change of variables and like correct everything and make everything look nicer, in the end, we've picked up 3 negative 1s, right? Negative 1 cubed is negative 1, right? But this piece is exactly the same as this piece, right? So using the fact that f is an odd function, if we try to compute this constant term a naught, what we end up seeing is, well, if you go through the integral, you're going to get minus this integral plus this integral. So they cancel out and you get 0. Okay. So the kind of observation or the intuition that, right, an odd function shouldn't have even pieces in its Fourier series, right, we also get quantitatively by actually trying to compute these coefficients. Okay. And so a similar proof will hold if you try to compute a sub n. Right, what will happen there is you'll have like a cosine term showing up right here. And so when you go from x to negative x, you're going to have a cosine of minus n pi over lx, which of course is equal to cosine of n pi over lx. And so you're not going to pick up any extra negative signs. You're still going to get 3 negative signs showing up in front. Okay. Yeah, okay. Right, and so, yeah, so as I mentioned, similar computation, we can show that these coefficients a sub n are all equal to 0. And so writing that rather explicitly, we have that, well, if f is odd, or we're looking at the odd extension of a function, then the Fourier series of f looks like this, where we can compute these coefficients like this. Okay. So one note is that, so in a sense, these two expressions give the same value. It's just depending on your setup, you have to be a little careful with what you're computing. Okay. This expression, I'll say, works best for f on the interval 0 less than x less than L. Or works best when f is defined just on that interval. This works best for f on minus L x, for x between negative L and L. Okay, the distinction is that, right, so if you take an odd extension of a function, if you work with this definition, you have to be a little careful that the function f you're plugging in is actually the odd extension. Okay. which we'll see an example of, or kind of we'll draw down an example here in a second, okay? But as a rule of thumb, if the function that you're working with is only defined on 0 to L, this is a safer expression to use. If your function is defined from negative L to L, I guess either works, but you might say this might be a little more safe. But okay, anyways. Okay, so let's see an example of this. And so maybe a little extra information should be here. So this would be on 0 less than x less than L. Okay. So what we can do first is sketch the Fourier series. Okay. This is 0, L. And so, right, if we go back a few slides, right, two ways of interpreting this. One is, sure, compute a Fourier series with only sine terms. The equivalent way is to first take the odd extension and then compute the Fourier series. Okay, so what we're going to do is we're going to take the odd extension of this function and then compute the Fourier series and see what we get. Okay, but the starting point is, well, let's sketch this. Okay, so if we're taking the odd extension, of course, we need to sketch that. Okay, so the odd extension, if we pick a point over here, what's its value? Well, look at the corresponding x over here. Look at the function value. It's 100. So the value over here is going to be minus the value we got up here. So the value over here is going to be minus 100. Okay. So this is a sketch of the odd extension of the function. So I'll write it like this. So this is the odd extension. And then if we want to draw the Fourier series, right, well, what's the procedure? Take the profile of the function, copy it over both ways. And so that's what we'll do here, something like that, etc. Okay. And so then the question is, well, what is the value of the Fourier series at points of discontinuity? Of course, that's the average of the left and right endpoints, or the left and right limits. And so in this case, the left, so here, the left limit is 100, the right limit is minus 100, and so then the average is 0. Okay. And so then this is the Fourier series, a sketch of the Fourier series. Yeah, series. Okay. And so the point I was getting at a slide ago here, okay, the information we're given is that the value of f is equal to 100 on the interval 0 to L. Okay. So if we try to use this formula, okay, the function that we're plugging in, this function right here is the odd extension. So what are the values of this function? Well, from negative L to 0, if we look at the sketch, from negative L to 0, the value of the function is negative 100. Okay. But looking at this formula, we just see f of x, right? Which we can go back and say, well, sure, that was the function that we started with, right? And so we run the risk of using the wrong definition of f, right? If you plug in f is equal to 100 on the interval negative L to 0, you're going to get an incorrect result. Okay, and so that was the point with, you know, be careful a little bit which formula you're using, depending on kind of the information that you're given about the function to start with. But anyways, okay. So that's the Fourier sine series of this function. And so the question is, okay, great, what are the actual coefficients? Right here, we're going to use this formula, right, from 0 to L, because that's where our function's defined initially. And so if you go through, right, well, b sub n is this expression, factor out the 100, compute the antiderivative, plug in at 0 and L, you're going to get this expression. Here, you can use the fact that cosine of n pi is equal to minus 1 to the n, which you can observe by like just sketching cosine of n pi or cosine of pi or x. And so then the coefficients we end up with, you can either write them just as this, that would be fine. Or if you wanted to clean it up a little bit, you could write it in terms of whether n is odd or even. Okay. Great, right? But this is what the Fourier series of the function 100 is, okay? Or the Fourier sine series 100, or equivalently, the Fourier series of the odd extension of 100 to the interval negative L to L. Okay. And maybe one point I can highlight here is that so computing the Fourier series of f of x equals 100 on the interval negative L to L, this will actually give a sub 0 is 100, a sub n is 0, and b sub n is 0. Okay, and so this would occur if, say, you use this formula and you didn't take care that this function was actually equal to negative 100 on the interval negative L to 0. Okay. So, right, when you're computing these coefficients, keep in mind what information you're given, right, what kind of decomposition you're looking for, etc. Yeah, okay. Okay, and so the question is, well, how might this stuff arise? Right, so one way that kind of this question can arise quite naturally is if you consider the heat equation with 0 boundary condition and initial condition equal to 100. Okay, and so going through separation of variables, right, our solutions we expect to look like this. And so for this to satisfy the initial condition, right, plug in t is equal to 0 so that this exponential becomes 1. And so you want to find coefficients b such that 100 is equal to this series representation. Okay, so one thing to keep in mind, right, so note that so the sum from n equals 1 up to infinity of b sub n times sine of n pi over L of 0, right? So note that for x equals 0, take the series, plug in x equals 0, this becomes the sum from n equals 1 up to infinity, b sub n times 0, which is just 0. Okay. On the other hand, f of x, especially if we're defining this initial condition at x equals 0, right, so this Fourier series is going to be 0, but the value of the function, the initial condition is going to be 100, which is not 0. Okay, and so this comes back to the distinction between a Fourier series and its and the function that kind of we're computing the Fourier series for, right? A function may not equal its Fourier series. Usually it does, right? And it does wherever the function is continuous. But as soon as you have jumped, or as soon as you have jumped discontinuities, the value of the Fourier series is not equal to the value of the function. Okay. The thing to note, though, right, is that, well, the Fourier series says that at x equals 0, say the value is 0. Okay, and so if we go back to our boundary conditions, that's exactly what we want from our function, right? The value of our solution at 0 should be 0. Okay, So the Fourier series works well with boundary conditions. It's just a little wonky for the initial condition. Okay? But one way to kind of get around this is to say, well, what's actually happening when we're computing this sine series, this Fourier sine series? What we're doing is we're taking the odd extension of 100 to the interval negative L to L, okay, like what we did here, right? So we're starting with this initial condition. We want a sine series. So implicitly what we're doing is taking the odd extension. And so if we take the odd extension, right, the value at x equals 0 will now be 0. Okay. Which works exactly well with, right, the question that we're trying to solve. Okay, right, so the Fourier series, I mean, they work well with the equation, they solve it, and that's really what we want out of everything. Yeah. Okay. So one interesting kind of phenomenon that can show up is if we say, okay, well, great, we have this Fourier series for this function, say 100. How good of an approximation is this, right? So here we're saying, well, take the sum of infinitely many terms, okay? But what if instead we took the sum over with just finitely many terms, right? Especially if we're trying to kind of compute these things numerically, right? Or yeah, numerically and with a computer, right? A computer cannot sum up infinitely many pieces. So, right, if we want to visualize these things and compute these things, we have to set a threshold of, only incorporate the first like 100 or 1,000 terms in the summation. Okay, so the question again is, right, how good of an approximation is this representation if we only sum up, say, the first n pieces? Okay, and so that's going to play into this phenomenon called Gibbs phenomenon. Okay, which I'll highlight in the next slide. Okay, so right, what we're doing here is we're saying, well, okay, our initial condition, or the function that we're trying to approximate, 100, right? That's going to be approximately this expression where it's like the Fourier series, except we're only adding up the first n terms. Okay. So if we only take, so all of these are off by 1, but whatever. If we take just the first term in the series, right, so this is going to be sine of pi over Lx. I think in this case, L is pi, but whatever. So if we just take the first series, right, it's 0 here, 0 here. It's kind of like that. And is it a good approximation? Maybe it could be better. And so then what we do is we say, okay, well, take 2 terms in this Fourier series, right? So here that should be 2 or 3. Just here, just ignore this terms in series business. If we take 2 terms, what we're going to end up with is this is now our approximation. Okay, so maybe it looks a little better than this, right? You're filling in more space. It's a little closer to flat up here, but not super perfect. Okay, take a few more terms in the series. Now you're going to get this approximation. Okay, so again, it's 0 here. It's closer to these boundary pieces at the ends, and up top it's overall flatter. Okay, so right, it looks like we're getting a better and better approximation as we incorporate more terms in this sine series. Okay, but how far can we take that, right? So add a bunch more terms. It's still 0 here. Up here, it's very flat, especially over here. But you'll notice that near these kind of discontinuities, it's starting to jump up a little bit more than it did before. Okay. And so then if we take about 100 terms, or right, even more, you'll notice this interesting behavior where, it jumps up and like it peaks up over here. It's really, really flat there. And then there's a weird gap kind of right there. And so what's actually happening here is how we're drawing this curve, right, we're not using a high enough resolution to actually see kind of the behavior. Okay. And so instead, what we'll do is we'll zoom in just over here, take a higher resolution grid over here where we're evaluating the series, and then see what we end up with. Okay. And so then, so if we zoom in about here, and this, and then plus a higher resolution, we get this image at the right. Okay. And so you'll notice that, sure, it's like kind of flat, but it's really, really jagged. And especially near the corners, like this gap is at least what, from 100 to 110. Okay. So near these points of discontinuity, this Fourier series is incredibly oscillatory, right? It's really jagged, and kind of the peaks, right, that we're getting, they seem to be getting higher and higher, or have a higher and higher magnitude, right? So over here, maybe the scale here isn't too great, but yeah, here it seems kind of a jump. Maybe it's about 10, but certainly what's interesting is, right, near the points of discontinuity, we are getting these massive jumps. And so the fact that the Fourier series is, you might say, like very badly behaved at these points of discontinuity, right, like right there, this is what's referred to as Gibbs phenomenon. Okay. So if you want to measure how good of an approximation you have just by taking kind of the maximum difference between your approximation and the actual function, this is going to give you a relatively bad error because it's going to tell you that the maximum difference is about 10, fairly large. Okay. But there are other notions of kind of size or distance between functions that we can use that this oscillatory stuff doesn't actually matter so much. But that's topics of discussion for another day. Okay. So let's look at another example. So here we want to compute the Fourier sine series of f of x equals x. Okay, so kind of how do we interpret what we're given? So this is saying compute the Fourier series with just sine pieces. So implicitly, you might say, well, this is a graph of f of x equals x on the interval 0 to x to L. And so what we want to do is first take the odd extension. Okay. X is an odd function, so the odd extension is just itself. It's fine. So once we've taken the odd extension, then we sketch the Fourier series, which corresponds to, right, translating the profile over, and then at points of discontinuity, marking the average of the left and right limits. Okay, so this is a sketch of the Fourier series of f of x equals x, or equivalently, a sketch of the Fourier sine series for the same function. And then, of course, we can go through and actually compute coefficients. Right, so we want a Fourier sine series for f of x equals x. So we want to say, well, x is a function we care about. We want to find its Fourier series. And so if you go through the steps, right, what are these coefficients? Notice that we're using this integral from 0 to L, because implicitly we're only given information about here because we wanted a sine series. So we're going from 0 to L of our function times sine. Go through the steps. You should end up with this expression. Okay. Okay. I mean, in this case, right, you could also use the formula negative L to L of x sine of n pi over L x dx. And this is because, right, the function x is its own odd extension, right? Take the odd extension of this piece, and you have the same definition for the function. So in this case, either of these would work. But anyways, okay, so let's look at one more example. So here, we want to compute the Fourier sine series of the function cosine of pi over L x, which already is interesting, right? Because we're saying, well, right, when we compute Fourier series, we usually have a sine series or cosine series or a cosine series. But here we're saying, right, take one of the terms in your cosine series and decompose it in terms of sine terms. Okay. Okay, so what does this look like? So what does this function look like on the interval 0 to L? Right, so cosine of pi over L x, and then you plug in x equals L. This is cosine of pi. What is the sketch of cosine? It looks something like that. So that's 2 pi. This is pi. This is 0. So the sketch of our function on the interval 0 to L is going to look like that. Okay. So if we want a Fourier sine series, okay, implicitly what we're doing is we're taking an odd extension and then computing the Fourier series of that. So we need to do is figure out what we need to do is figure out what the odd extension looks like. So if well, let's see. So as you kind of approach x equals 0 from the right, the limit should be, so kind of in this domain of definition, the limit is equal to 1. So for the odd extension, right, if you approach like that, the limit should be negative 1. Okay, so you expect the function to look something like that. Right, but there are a few other ways that you can go about trying to sketch this, but what we've sketched right here, this is the odd extension of cosine of pi over Lx. Okay, and so then if we want the Fourier series, well, just copy this profile over and then mark an X at every point of discontinuity. Okay. Great. So we've sketched what the Fourier sine series for cosine of pi over Lx looks like. Now, of course, the question is, well, what are the actual coefficients? And so those are things we can compute, right? So we want to write cosine of pi over Lx as a sine series, sine series. So the coefficients, this, keep in mind here, right, the bounds on the integral. If we integrated from negative L to L, then all of these coefficients would be 0 from or due to the orthogonality conditions on sine and cosine. Okay. And so we really don't want to integrate from negative L to L. Okay. But another way of thinking of this, right, is, well, our function was only given to us on the interval 0 to L. And so that's really the only information we have to go with in computing these coefficients. Okay. So in any case, these coefficients b sub n, we have this 2 over L, integral from 0 to L, of the function we care about times sine of n pi over Lx. And of course, go through the steps, do the integration. You should end up with this. Okay. Yeah. So, right, takeaway for all of this is, if you ever see, right, the phrase compute the Fourier sine series, implicitly what's happening is you're being told to, one, take an odd extension, or take the odd extension of your function, and then compute its Fourier series. And then because you're working with an odd function, the Fourier series will only consist of odd pieces, and so you're only going to have sines showing up, sine terms showing up. Okay, cool. So the other piece then is talking about Fourier cosine series. Okay. And so it's more or less exactly the same thing. It's just replacing sine with cosine, replacing odd with even, etc. Let's see what that looks like. So if your function is defined on the interval negative L to L, and your function is even, then if you take its Fourier series, you'd expect that the only terms that show up in the series are also going to be even. Okay? Cosine is an even function, so that so your Fourier series should only have cosine terms, right? Now, if instead of f being defined on this entire interval, if you only know the values of f on the interval 0 to L, right, the question is, well, right, what are the Fourier coefficients? And so kind of two approaches we can do. One, we can go ahead and compute the Fourier series on this interval, where we only compute kind of the cosine coefficients, or equivalently, we can first take the even extension of f to the entire interval, and then compute the Fourier series of the even extension on this entire interval. Okay, and so again, they result in the exact same series. And so implicitly, if you ever see, right, compute a Fourier series with only cosine terms, implicitly what you're doing is you're first taking an even extension and then taking the Fourier series on kind of that entire interval negative L to L. Okay. So what is an example of this, right? So here we're told, well, compute the Fourier cosine series of x. Okay. So we're told compute the Fourier cosine series. So we're told compute a series only using cosine. So implicitly, right, this generally arises if we only know the function on the interval 0 to L. On the interval 0 to L. So what does x look like over here? It looks like that. And so now what we want to do is say, okay, well, if we want to compute a Fourier cosine series, implicitly, what we were doing is taking an even extension and then computing the Fourier series of that. Okay. So what we're going to do first is take the even extension of this function. So what does that look like? Well, right, take a value over here. What's its value? Look at the corresponding x over here. Look at the f value. That f value gets copied over. So even extension is going to look something like that. Cool. So that's this is the even extension. And so now if we want to sketch the Fourier series for this even function, right? Well, just copy this template over. It's going to look something like that, something like that. Okay. And then at points of discontinuity, we're going to mark an X. Okay. Here, in this case, though, right, there are no points of discontinuity because this even extension is continuous. And then the values at the endpoints, right, the left and right limits agree. So we don't have to mark any X's. Okay. So this is the Fourier series of the even extension of X. And what we can do is actually explicitly write down. So, right, for f of x equals x, right? Well, right, so let's compare how this kind of problem differed from, where was it? Way back over here, right? So here we took the odd extension and we got something like that. Over here, we're taking the even extension and getting something like that. Okay. And so in this case, we can say for f of x equals x on 0 less than x less than L, so on just this half interval. So the even extension is the absolute value of x, right? That's what gives this graph. Whereas the odd extension is just x itself. Okay. Cool. And so in this case, right, well, even extension is a little easier to write down. So if we wanted to, we could use kind of this function definition on the interval negative L to L when we're computing coefficients. So let's see what that looks like. So what we want to do is compute the Fourier cosine series of this. In other words, we want to write x as a cosine series. Okay. And so if we compute coefficients, well, right, that constant term is going to be the average value of the function over the interval for which this function is defined or for which we were given information about it. And so the constant term is going to be L over 2. Otherwise, right, these other coefficients, same interval here, 0 to L, it's going to be your function times the cosine piece, and you can show that that's equal to that. Okay. So one thing I want to highlight here is, well, another way to compute this coefficient would be 1 over 2L, the integral from negative L to L of the even extension of this function, which we saw was the absolute value of x. Okay, so these two integrals, or these two kind of things, they'll give you the same number. Okay. Likewise, for a sub n, we could also compute it as 1 over L integral from negative L to L of the absolute value of x times cosine of n pi over L x dx. And that would be fine, because again, right, what we're doing here is we're explicitly writing down the even extension. The even extension is what we're computing the coefficients of. Okay, if you wrote x here and then integrated from negative L to L, you'd get the incorrect kind of answer, right? Because you wouldn't be working with the even extension of x. Okay. Yeah. Okay. Cool. So the last thing to talk about is a little more kind of how these Fourier series relate to these notions of even and oddness, and in particular, we would like to say something about continuity of these series. Okay, right. So if we flip back to the examples we saw here, right, we took this cosine series; it was continuous everywhere. Whereas generally, for these sine series, these had a lot of discontinuities, right? Okay. So the question is, right, are there properties of even and oddness that can determine whether or not your Fourier sine or cosine series will be continuous? Okay. Right, so keep in mind that, right, as we said before, any function f can be written as an even and odd, or the sum of an even and odd function. Okay. And so the other kind of observation is, well, when we take the Fourier series of a function, or of a sum of functions, the Fourier series is a linear operation, right? So, in other words, the Fourier series of, say, f plus g, where f and g are some functions, this is the Fourier series of f plus the Fourier series of g. So because we can write a Fourier series in terms of an even odd function, and when we take, because we can write any function as the sum of an odd and even piece, and because taking the Fourier series is a linear operation, if we want to know the Fourier series of f, it turns out that the Fourier series of f is going to be the Fourier series of the odd piece, which because we have an odd function, this is just going to be a sine series, plus the Fourier series of the even piece, but because this is an even function, the Fourier series is only going to have cosine terms. Okay, so yeah, the Fourier series of a function is going to be the sine series of the odd piece plus the cosine series of the even piece. Yeah. And so keep in mind here, right? So here, implicitly, this is for x on the interval negative L to L, right? Because we're just taking the Fourier series of everything. In particular, these functions f even and f odd, these are not extensions, right? These are functions that we can compute, that we can construct from whatever we're told f is, right? And this was, so f even, this was f of x plus f of minus x over 2. F odd was f of x minus f of minus x over 2. Okay. So these are the even and odd parts and are not extensions. Okay. Great. Yeah. So yeah. So the other piece I was getting at was continuity, and so that's, I guess, different section and the last section. Right. So in general, if you have a piecewise smooth function f, okay, we can compute its Fourier series. And the Fourier series of f will be continuous and converge to the function wherever the function is continuous. Okay. Right, wherever the function has discontinuities, the value of the series is going to be the average of the left and right limits. Okay, so you get that discontinuity. But wherever the function is continuous, the Fourier series will converge to it. Right, you'll get equality between the function and that series. And so the question is, okay, well, right, if you have a function that's continuous, say negative L to L, maybe it looks something like that. Okay, so sure, this function is continuous in here, but as soon as you sketch its Fourier series, right, you're going to get this discontinuity right there. Okay, and so the question is, well, if we want everything to be continuous, right, how do we avoid these bad bits? Well, to avoid this discontinuity here, we need the left and right limits to agree. And so in particular, the value of f kind of over here, which is that same value, needs to be equal to this value, right? So if we have f of minus L is equal to f of L, and f is continuous kind of on the interior, then there are going to be no points of discontinuity, and so then the Fourier series will equal, right, the function itself everywhere. Okay. And so the question is, well, great, this is a condition we need to kind of ensure so that the series is continuous. And so what we can do is we can say, okay, well, what happens, right, when we compute these Fourier series, right? So the observation is, well, because cosine is an even function, right, cosine of negative L, or cosine of n pi over L of negative L is equal to cosine of n pi over L of L, right? And so this condition, this condition is satisfied for all of these pieces. And so in particular, the Fourier cosine series of the function will be continuous if and only if your function is continuous. Okay. Right, and so maybe another illustration of that will be, right, so let's see what that looks like. So say you're only given the function in this interval. Okay. So what we do is we compute the even extension, right? That's just reflecting the graph of the function across the y-axis. And so in particular, values over here are going to be reflected over there. So your function is going to be continuous right there. And then you get something like that. Okay. But the other thing is, well, okay, what is the value of the even extension here, right? Because we're working with the even extension, we're defining f so that this holds, this condition holds. And so in particular, if you plug in L, right, that's how it reads. And so the endpoints agree. And so then when you take this this Fourier series, it's going to look something like that. Okay. So at these endpoints, right, which is one possibility for kind of these discontinuities to appear when you compute these Fourier series, at these endpoints, you don't get these discontinuities. At x equals 0, you don't get any discontinuities. So for this Fourier series to be continuous, okay, the only way that this can break is if the function that you started with was discontinuous in its interval of definition. And so an example of that might be the following. So suppose this was our function that we were interested in, okay? And we take its even extension. It's going to look something like this. Okay. Right, that's the even extension of the function defined here to this entire interval. And so if we sketch the Fourier series, it's going to look something like that. And then discontinuity here, and then something like that, and then like that. Etc. Okay. And because we had a point of discontinuity in here, right, the Fourier series, the value is going to be the average of the left and right limits, so we mark an x there. Okay. Right, but notice this point of discontinuity when we looked at the Fourier series, that only arose because of discontinuity in here, right? The way that we were extending the function, there's no issue there. And the way that we were kind of taking this periodic extension, there is no issue there. The only issue was that it was discontinuous on the interior. Okay, so as long as your function is continuous, where it's defined, then the Fourier cosine series will also be continuous, and you'll get convergence everywhere. And so in particular, you can write down exactly that f of x is equal to a sub 0 plus sum from n equals 1 up to infinity, a sub n cosine of n pi over L x. Okay. Cool. So that's cosine. So what about sine? Right. So the same statement from before, right? If your function f is piecewise smooth, its Fourier series is continuous and converges to the value of the function wherever the function is continuous. Okay. And so the question is, okay, well, if you take a Fourier sine series, I mean, what happens there? So the claim is that, right, if your function f is piecewise smooth, then its Fourier sine series will be continuous and it will converge to f in the interval you care about if and only if your function is continuous and the value of the function at 0 and L, kind of right where it's initially defined, these are both 0, right? So it's not enough to say that, right, you just need the functions to be equal. You need them to be equal to 0. Okay? But if that's the case, then right, your Fourier series will be continuous and it will converge to the function everywhere. Okay, so as before, right, what does this look like? Well, suppose your function is defined from 0 to L. And so let's just start with something. Let's say this. Okay, so we want f to be continuous in the interior, okay, because otherwise we're going to have a situation like this and we're going to get these discontinuities in the Fourier series. So we want our function to be continuous in here, okay? But what we're going to do is look at successively what happens if, right, this kind of doesn't hold, okay? So suppose your function is 0 at x equals 0, and then it has some value over here, okay? Well, if we take the odd extension, it's going to look something like that, okay? And so then if we compute the Fourier series, right, we need to take the periodic extension of this. So we're going to get something like that, okay? And so we see here, well, this value, let's say, right, so here's the discontinuity. And so how is this arising? Because f of L was not equal to 0, right? We want the left and the right limit to agree. But because we're taking this odd extension and the periodic kind of extension, well, what's going to happen if this value is non-zero, right? What's the other limit going to be? Well, it's just going to be minus this limit because of how we've constructed this extension. So the only way for this limit to agree with this limit is if this value is 0, right? Okay, so let's draw an example of that over here, right? So what we're going to do now is say, well, what if it's 0 at L, but non-zero at 0, at x equals 0? So if we take the odd extension, right, we reflect the graph and then reflect it across the x-axis. And so here, right, well, what's the value over here? It's going to look something like that. And then maybe something close enough. Okay. Actually, maybe I should have done green. Okay. So that's the odd extension. Now we can take the periodic extension. So what we're going to do is, right, copy this profile over a bunch. So we're going to get something like that, etc. Question is, where are the points of discontinuity? Well, because f of 0 is not equal to 0, when we took this odd extension, right, the value over here is going to be minus the kind of the value there. So we're going to get a discontinuity there, etc. Okay. And so right here, this is illustrating that if, well, f of 0 is non-zero, you can also get a discontinuity that way. Okay. So if you don't want any discontinuities showing up in your sine series, right, the function that you're starting with better be equal to 0 there and there, and it has to be continuous on the interior. Because as soon as you have that, right, when you take the odd extension, something like that, and then the periodic extension, well, now this value gets copied there, and so you're going to get something like that, etc. Okay. Cool. So generally, if you take a cosine series, those are the good ones. They're continuous. They're well-behaved. You don't need a whole lot of conditions on the function's values to get some decent results. On the other hand, sine series, if you want the Fourier series to be continuous, you need to ensure that the value of the function is 0 at x equals 0 and x equals L. As soon as you have that, then yes, take the sine series. The resulting series will be continuous. And that's it for this section.